This is actually a brand new talk for me. I've never given this talk before, so you're going to notice me stumbling about a little bit. And in fact, I was still putting together the rationale and the slides a lot last night. And at some points, I thought it would be easier if I just gave someone else's talk. It was very tempting. And actually, when you just think back to the last two talks that we just saw, it's actually surprising that it wouldn't have been that odd for me to give those talks, either one of them, because there were a lot of elements in Nick's talk that also appear in here, although perhaps from a slightly different angle. And there were, well, I would just say that there have been times when I've given basically Demis's talk, but perhaps not with the angle of trying to create AGI, but just to try to teach people who work in AGI why it's important to look at parts of the brain and how the modularity matters and things like that. That's stuff that I did at AGI 10 and other conferences. So those are all very familiar. So was I just trying to give someone else's talk? It turns out that, in fact, I am going to give someone else's talk to a large degree, because Suzanne Gildert was supposed to be here to give a talk, and it turns out that my talk depends a lot on the material that was going to be in her talk, so I'm pretty much going to have to go over her stuff as well. I have started looking more at the rationale that's behind substrate-independent minds or whole brain emulation. And when I talk to a crowd that's interested in life extension, then I start by talking about what is the fundamental stuff that you're really interested in? Why are you doing this? Nobody just wants to live longer. You know, that's not why you do it. You want to live longer because, well, in my case, it was because, you know, what I really want to do and what I enjoy is to try to understand everything and to try to create anything. So from a life extension point of view, that's why you would do this kind of stuff. But here, it's more from the machine intelligence point of view. So let's see how that relates. Okay, this is just the overview. So I'm going to talk a bit about universal Darwinism, then about competitive intelligence, and then the substrate-independent minds comes in. I won't stick with that for too long right now. Okay, so I'm going to try to take a long-term view. And in fact, I'm not just going to talk about the evolution of algorithms in machine intelligence and where that's going to go in the future, but I'd like to look at the evolution of thinking in general, and how does that depend on competition? How does that depend on what we might call universal Darwinism? That's a well-known term. So what I want to do is take a perspective that looks at it from the likely outcome, a logical or reasonable outcome, and look at it from that angle and see, well, where are the best possibilities there given our interests? So the other part is the perspective of our interests. And taking those two things together, I'm going to propose the significance of a specific subset of AGI. And you can probably guess that I'm going to talk about substrate-independent minds or whole brain emulation there, which is that subset that I mean, of course. Okay, so if we look at a specific piece of knowledge, we could say that a specific piece of knowledge can be adapted to a certain niche in the environment or universe. And within that niche, it's embodied in some substrate. Okay, substrates or materials. And now, for example, well, to give an example that is very close to home, that's also from my work, is of course that this could be the knowledge in, let's say, the code, the DNA that's in our genes, and that's the substrate in which it is embodied, is a bunch of sugars and carbons and things like that. This pattern persists, replicators replicate, and in general everything competes. That's the whole Darwinist view. And in the end result, what you end up with is that, okay, some things or some, I talk about entities, but when I talk about entities, I really mean classes of entities, because these are evolving things. These are things that adapt and change slightly. But the ones that sort of descended from, well, there are certain lucky ones that end up occupying more space-time than others. And maybe that's even a measure that you could take for success. Because what is success in competition or in universal Darwinism? Well, maybe it's just how much of space-time do you occupy, or in how much of that can you find that class of entities. So these successful components occupy more of that, and a well-adapted entity's knowledge causes its niche to maintain that knowledge. Again, the example close to home is, for instance, the human body being the environment that our gene survival is good at, at living in, and which maintains that knowledge by, basically procreating. Okay, so every time a replicator replicates, it doesn't just work with some sort of knowledge, it works with material. And that material is non-replicating material. In the case of the human DNA, well, say carbon, for instance, is a very important material in there, but this is non-replicating. Carbon itself doesn't replicate. Non-replicating knowledge can be embodied in different physical substrates each time. Now, if we take competition in universal Darwinism, we put all that together, we could say that sometimes some substrates are safer than others, given conditions. So I'll hypothesize that replicators can survive better if they move to safer substrates. And it's not really the matter that counts, it's the knowledge and how that survives. Okay. So a result of natural selection are biological reward mechanisms which lead to greater survival. And, well, what are aspects of this survival? Well, one of them, let's describe utility functions and reward functions. Utility functions being that basically a long-term function that describes what you're trying to optimize towards, what you're trying to achieve, sort of your built-in purpose. And the short-term reward function is that which you react to quickly in order to try to stay on that utility function. So these are mechanisms that help you do that. And if you look at what's actually going on inside our brains, for example, neurologically, what is it that actually happens there that embodies these reward functions? Well, these are some excitable or suppressible loops, basically. So you've got, and you can extend that into other areas and say, well, maybe something can be excited or suppressed, and that's a way to mechanistically express what a reward function is. So entities with different utility and reward functions, they compete with each other, sometimes for the same resources, sometimes just because they happen to be in one another's vicinity. And in a world of entities that are trying to ensure their survival, if you happen to be the only one that is not doing that because you don't have a self-consistent reward mechanism, then you're not going to be around for very long. Basically, you perish. And by the way, another way of realizing that this is a very new talk for me is that there's still way too much text on every slide, so be warned. Okay. So what do we learn from this, and how does this relate to the fundamentals of AGI? There are some fundamental questions there that I think that still deserve more research, and it so happens that Suzanne recently took on the challenge to look at those from a universal Darwinist perspective, and I think that her insights there are quite significant. And not entirely coincidentally, I also started thinking about those just a few weeks afterwards and came to almost the same conclusion. So I think that's probably why I kind of like what she's saying, which is that in a universe with these organizing factors of competition, it may not be possible to have super intelligent, truly general AI. And it may also be extremely difficult to enhance our own intelligence, to improve it in any way. Now, why is that? Okay, let's start with those reward mechanisms again. Humans can understand that they obey intrinsic reward mechanisms, that we have some built-in intrinsic drives. I mean, we understand this because we've begun to understand more about our own biology and how we work. I think that to be generally intelligent, you also need to be able to learn about yourself. Now, just as an example there, even other things like Gödel machines do this to try to be more optimal, to be able to improve themselves. So I think that other intelligences at human or greater levels of intelligence would also learn to see their own intrinsic reward mechanisms, or to at least know that such mechanisms exist. Now, if you know that they exist, okay. If you want to be totally generally intelligent, so you want to be able to handle all kinds of new problems in new domains, you need to be able to adapt to all sorts of environments. And not all of the domains are served well by the same reward mechanism. So in addition to understanding that you have these kinds of reward mechanisms, super intelligent general AI, in order to fulfill its most useful purpose, which is to be super intelligent, otherwise why would you generate something like that, can't really have a fixed reward mechanism. Also, intelligence is very good at slipping out of these boxes that you try to capture them in, let's say. So intelligence can learn to affect that which specifies its utility function. Let's say that you've tried to make a fixed utility function. You don't give the superintelligent any tools with which it could change its own utility function. Then, well, either it's not going to be super intelligent and general because it can't change its utility function, or if it can, then it can do so by virtue of coming up with a way to get around that problem of having a fixed function, which is, for instance, social engineering. So then those fixed functions for these kinds of AI are not really fixed. And where do we see that this is something that an intelligence would like to do? We can look at ourselves. We already think that it would be interesting to enhance our own intelligence, to enhance ourselves, to be able to allow us to modify our own reward functions if necessary. So I think that some entities will gain the ability to modify their reward mechanisms. And we're probably one of those. Okay, now what can you do if you can modify your reward function? Well, one of the things you can do is you can try to continually maximize it over time. This is something that's been discussed before in the context of what AIXE might do, for instance. And, well, you could use new information to try to redefine your reward functions. And obviously, the one thing that you can do immediately is set your reward exceedingly high and set your goals such that attaining the rewards is very easy. And just as an example here, I've taken from science fiction, from Permutation City, there's a character in there. I don't know how many of you have read this, but those of you, okay, at least Toby's read it, that's good. Oh, more people, yeah. Fingers are going up. There's a character in there called Peer who basically does that. Just in order to keep on living and have a motivation to survive, he just changes his reward function, he changes his utility function, in fact, not just the reward function, but his utility function, such that he has different interests that are completely fulfilling while he's doing them. And at one point he just basically, I think it was table legs, wooden table legs that he keeps on making, and he's totally blissful doing this. Okay, I'll have some water. Okay, so if we assume that it's possible to maximize your reward over time like this, and there's this Darwinian necessity for a self-consistent reward mechanism, then a problem is that as you start changing a reward mechanism, an entity can adopt behavior that corresponds with a nihilistic philosophy. So a philosophy in which you understand that you can change your reward and your goals any way you like, so there really is no purpose. And I mean, we're already at this point. There are so many people in this room right now who already believe and understand that there is no universal purpose anyway. So you can, you can set these goals any way you like, except that we already have some intrinsic drives that are setting them for us right now. Now, if you do that, there are a number of things that can happen. You could be dialing down your feedback, your reward feedback, so that you no longer get the necessary suppression or excitation that you need to properly, be competitive and survive. Instead, you might be more catatonic. You might just be very passive. And I'm going to show some examples in a moment of how this can actually happen in humans through lesions. That's very interesting. Also, another possibility is that you realize that all of these actions, all of these possible reward mechanisms are equally purposeful from some objective point of view. So you could choose any one of them, and at some point you might happen to come across self-termination. It might even be your first choice because it might seem the most logical at that point. Well, it might just be that these reward mechanisms chosen through some arbitrary path are statistically inferior to those of some other entities that you're competing against that have more strongly grounded reward mechanisms and that compete better for resources and survival. So, given that instability, where you then lack a requirement for adaptation, if we lack a requirement for adaptation to begin with, we lack the criteria to distinguish the desirable from the undesirable developments. So, prior to any selective pressure being put on this AGI, you can end up with a utility function that's basically the result of a random walk, and the evolution of AGI becomes a random generator of some sort. So either you get stuck with something that's optimized to some utility function that is therefore not quite general, or you begin with an intrinsically general and therefore either catatonic, self-terminating AGI in this case, or you end up in some arbitrarily discovered niche. So that's basically the proposition that Suzanne came up with as well. Now, given that those postulates about superintelligent general AI, okay, let's say they're true, in that case, the only kinds of AI you end up with, or let's say close to superintelligent AGI, would be aberrants that ended up in some competitive parameter niche. So they're still competitive enough to have survival capabilities and to operate meaningfully. So they're going to compete, and they're going to compete against other entities for resources. And this could be something that we don't like if they're competing against our interests and if they are fairly good at replicating and relatively intelligent. So the operating survivors wouldn't be called friendly superintelligent general AI, and they don't go around solving all of our problems and extending our existence. And there's a reason why I have a bit of a pet peeve there, which is that I really have nothing against AGI. I like working on AGI, I like thinking about AGI, but I'm not religious about it in the sense that I don't go around saying we're just going to build all-powerful, super intelligent, friendly AGI and it's going to solve all of our problems. It'll make us happy and it'll even give us mind uploading. This is literally something that I've heard many times, and it's rather annoying actually. So I think that if you're too religious about any of these things, then it tends to divert valuable thought and resources into the wrong areas. Now, so that's as far as I can go with just theorizing about this and rationalizing it. But I think that at this point we do have to actually build things to learn more and look over the horizon, so I will definitely agree with Demis there. Okay, what do we do with this now? So we've looked at the case of AGI. So gene survival, though, which is what we're stuck with right now, is a highly environmental, or is highly environment dependent. It's really in a niche. So the environment that it is optimized towards, this particular niche, in our case, our biosphere here, is always at risk. I mean, it's a single environment, anything could happen. It's very easily annihilated. And I know that there's a wonderful book edited by Nick that's about catastrophic risk that shows us many ways in which we could be wiped out right now. So gene replication itself won't be a significant universal survivor, given enough time and possibility. Intelligence that's adaptable to many challenges is highly competitive, though. So my, I guess, statement here is that I think that the evolved descendants of the most competitive entities occupy most of space-time, at least when we're thinking about which proportion of intelligent entities would that be. Competition is an evaluated result of an interaction, and we're looking at it from a temporal perspective. I mean, how else do you evaluate who's the winner in a competition? We look at two entities that are interacting in some way, and then which one of them ends up with a bigger share of something, mostly time, for instance, if the other one perishes. So that's one way of looking at it, take a temporal perspective. So which one dominates the largest stretch of time into the future? So I'm trying again to look at this from the end result. So what's consuming most of space-time? And I think that it would be the intelligences that can adapt to many environments rather than the ones that are stuck being adapted only to something extraordinarily specific. Now, our intrinsic drives still seek gene survival. That's what they were evolved towards. This is what the reward mechanisms are in place for and optimized towards. It's a very specific environment, and those mechanisms are self-consistent, so they're giving us the desire to carry out specific actions in accordance with local goals. It's finely tuned to that local competitive environment, and it's not just competitive. I mean, there's, of course, cooperation, and there's a sort of kin selection that goes on as you choose your levels of cooperation, but when you take a larger group, you still see that there is competition overall. So changing our intrinsic behavior could lead to conditions that no longer favor survival. This is the idea that around this optimized point in which we exist, this optimization towards having a reward function that really makes us competitive in this environment, is a landscape that's really unknown, it's uncharted, but that may very well consist of a lot of areas in which our survival would not be very well guaranteed. So there's no smooth transition to another set of reward mechanisms, let's say, that also guarantee such survival. And this is something that we call a catchment area. And I would like to say that I consider it a protective trap, as in if we assume that there is this high-risk landscape, and we also assume that the instability I was talking about before is an issue, that when you change your reward mechanisms, you might end up in some not so competitive, not so survival-oriented situation, but that you do need self-consistent reward mechanisms, then we could say that you exist in such a catchment area of an evolved reward mechanism, and it's providing you with a self-referential purpose. Even though there's no universal purpose, it's giving you some purpose that you're continually striving towards. This is what's defining your utility function. Okay, so what can happen? What evidence do we actually have in humans that there is such a utility function that's been evolved into such a catchment area, and that bad things happen when you tamper with them? One of them is when you look at the anterior cingulate cortex and lesions in there. This is an area that's critical to pain, error detection, emotional suffering in others, and also your own emotional suffering. Now, if you damage that area, and I'd like to thank Tom Michael, by the way, for this slide. We talked about this for a little while, and he said he had some really interesting data there. You see that the people who have lesions in the anterior cingulate cortex often end up more apathetic, socially withdrawn, and in some cases they even have a total lack of movement and speech. So basically what you're seeing here is kind of a removal of this self-referential purpose of a utility function, of a functioning utility function at least. It's not operating correctly. Okay. Now, related to this, in the orbitofrontal cortex, which is the area that we really use for anticipating reward. It happens to be an area that I used to model in, so I picked that one. There, if you have lesions, it's almost the same thing, but not quite. I would say that perhaps here we're impairing reward mechanisms rather than the entire utility function, because what you end up with is someone who is more indecisive, has impaired judgment, lack of planning or insight. So basically, doesn't have quite the right approach to going about their lives in a survival-oriented way. If they weren't in the care of an institution, if they didn't have a society around them that still protects them to a large degree, they could be in a lot of trouble. So, can you escape this catchment? I think that you can, but I think that the way to go about it may have to be a gradual approach, something careful, almost adiabatic. Other intelligences are going to compete with ours, and those could be either machine intelligences that don't have quite the same intrinsic drives, or they could be intelligences that originate elsewhere. I think that the prime competitors are going to be those that are able to adapt quickly, to change their strategies and their capabilities. Now, changing one's utility function is a powerful way to adapt, even though it is dangerous. So how can you modify those capabilities? Well, gene survival implies some of these reward mechanisms, of course. So one of the things that you may want to do is to transition away from an exclusive focus on gene survival. You want to escape the catchment area, but rapid changes are dangerous. And we don't really know how to pre-compute what's going to happen. So the outcome is that perhaps the best way is to take a gradual and tentative approach. Tentative in the sense that if you have a way of backing out of your choice, that would be optimal. Okay, so how can you actually do this? This is where I start to talk about substrate-independent minds. So I'll start by talking about the mind and computability. Everything computable is computable by a Turing machine. Okay. church-cheering. Neuroscientists have a consensus that our mind is basically a complex machine. I don't think that we're going to find too much argument with that. And these processes are computable, so then the mind also has to be computable. This is kind of Demis's point about algorithms. So our brains are machines, complex machines, but they are that. And every Turing machine should be able to implement another one. This is where whole brain emulation comes in. So whole brain emulation is based on this idea that you can emulate what's going on in your brain in some other substrate. So I call this the most conservative approach because there really are multiple ways of looking at how you would transfer a mind from one substrate into another or make it possible to exist in multiple different substrates. But whole brain emulation is the most conservative one because there you're simply taking the approach that you're going to re-implement all of the operations that are relevant to the functions that were originally carried out in the mind. So what you want to be able to do in the new emulated substrate is to be able to predict your next state of mind the same way as you would in the original brain with some small error. And I would say that re-implementing your brain's operations like that is even more conservative than taking a couple of modules or features out of it and implementing it in an AGI. One of the reasons for that is because the modules in the brain are very interdependent. They provide feedback to one another. So what happens when you just take a few of those and you try to make an AGI with those? It's not obvious that that's going to work. So the reason why you would want to do this, why you would want to do make it possible to transfer to other substrates and move away from gene survival only is because, okay, let's begin at the beginning here. Whatever's going on in our minds, this processing is really all that we are. It's what we experience. So this is really, it's the combination of perception, it's the combination of memories, executive processing, that's what's going on. I mean, we have senses that give us data, we have motor activity, and then the feedback from that, we've got our memories. But really, all we know is what we're processing. That's the whole experience we have. So that's what we're interested in. We're interested in the experiences that are going on now and the experiences that we can have in the future. We're interested in our individual notions of what those future experiences should be. So in future development, we have a characteristic way of working with knowledge. We have a way that we understand things, that we represent knowledge, or that we use it. And this can be different from one person to the next. So in a sense, the way that we do that champions certain memes. That's one of the things that we do with that. And those memes affect future development. So we can say that the universe, which is affected by successful pattern competitors, is also affected by such memes, and we have an interest to support the survival and competitiveness of patterns that are focused on individual specific thought. And I could just take, as an example, I can say that any one of you probably has a certain idea of what they would like the future to look like, and that view is in some way distinct from everyone else. So there's something very characteristic about your own thinking. So if we think of the mind as part of an environment that genes create to support their own replication and survival, which is really where the mind comes from, then we have something different than what we care about, because what we care about is the experience of the mind. There's really no particular reason why we should be strongly attached to a specific pattern of DNA, be that the DNA of a human or the DNA of an ant or some other creature. Since our interest is really in what we experience the whole time, which is just what goes on in our mind. So if we transition from a focus on genes to a focus on our interests, then we want to be able to find new modes of pattern competition with replication, adaptation, and propagation, all these features that we see in the gene survival that work so very well, except we need to do it differently. Genetic material carries with it the ability to enact the creation of environmental conditions that favor the replication and spread of its self-same code. The body is such an environment, and it aids the genetic replicators. So self-replicating properties of genetic material can be part of the substrate that compiles and emulates functions based on a pattern, even if that's not human DNA. I won't really go into the virus example here, because I think I'm already being too slow on this part of the presentation. Substrate-independent existence implies that one can devise compilers and emulators in various available resources to operate the relevant patterns in a manner that includes replicating, propagating, and adapting properties. So you're not just looking at copying the knowledge, you're not just looking at copying the pattern itself, you're trying to find a way to develop these flexible compilers and emulators that you require so that the knowledge is used in the same way that you were used to using it before. The objective of substrate-independent minds is defined as the search for strategies for the competitive survival of the patterns of our mind functions. So this substrate-independent minds embraces universal Darwinism and in fact seeks to build according to what we're assuming is its outcome. Substrate-independent minds provides a method to escape the catchment by finding suitable substrates with different optimal capabilities. And it deserves close attention and development because first of all, we're beginning to see candidate technologies that could be used to bring it about. And secondly, because I believe it has the greatest potential to actually help us be part of whatever survives or whatever is potent in that sense. So we need a way to be able to experiment and augment carefully to try out various modifications. That's a way to get out of the catchment area. We need to have access and interpretability of the mind, and whole brain emulation is a technique that at least solves that access problem. With that, you can explore and you can experiment. And that way, you should be able to find a route from one place of existence to another, unless there's some kind of discontinuity in there. So for example, you can experiment by seeing what happens if you run everything twice as fast. Or you can look at what happens if you try to plug in something like flawless memory, although that's a little more complex. And I assume that once you learn how to do this, our skills at hacking minds are going to get better, and eventually you might even learn how to pre-compute some of the effects. Well, I have one more example down there. Let's say you try out 1,000 tweaks at once, and you use some kind of winner-take-all evaluation based on capability and competitive survival. So what is the whole idea here? You start with the mechanisms that already support the experience of mind that we have right now, and you solve this issue of scope and resolution, which is still unsolved for mind uploading, whole brain emulation, and substrate-independent minds, three terms that are not quite the same but are related. But I won't go into that either right now. I do believe, though, that resolution and scope are all limited. I mean, it's clear that these are not infinite, so because they are limited, and actually I think they're quite limited, it is possible to emulate the mind at that resolution and scope. Okay, now I'm not going to go into this example either. That was just an example about how you might be able to say that using knowledge in one substrate is the same as using it in another. Okay. So let's look at a few technologies now. This is kind of going towards the end of my talk because this isn't really a talk about technologies to do whole brain emulation or to do substrate-independent minds. This was really about the rationale of why would you do it and how does it compare to AGI, etc. But I do think I should list at least the 6 technologies just because I said that there are some technological possibilities that we see now. And I'll start with whole brain emulation, and in fact I'll start with the structural approach, which is kind of the traditional one. It's one that most of the workshop that was held here in 2007 was devoted to. The idea is that after death, post-mortem, you take the brain and you basically slice it into very thin slices and image it, and then you can reconstruct it and reproduce the function inside it by inferring from the structure of the elements that you see, or through some other detection that you carry out as well in these slices, what the original function of those components should be, because you have some library and you can do a correlation between them. This is actually similar to reverse engineering CPUs that you sometimes find where they will open up a chip and they'll go and they'll image each of the layers, they'll kind of peel off the layers and image them and then recreate a chip in software and run it there. There are 3 main labs that are working on this technique. One of them is Denk, and the others Lichtman, Hayworth, and Cho. Now Lichtman is actually the head of that lab, but Hayworth is definitely the one who's put in most of the work on the technology. That's why I mentioned him separately. I'll show you a little bit in just a moment about those. One problem with this approach is that you do need to rely on the fact that there's some kind of one-to-one correspondence between structure and function, and that you can actually identify which function belongs to which piece of structure. So there's a matter of quality control there. You need to validate that what you end up with is actually the functional system that you want it to have. I personally have some qualms there because, as you know, I have some engineering background. You don't generally want to build a really complex system, which this would be, by building a huge complex structure based on these blueprints that you're scanning, and then just push the start button and hope everything works. That's not generally a very good approach from a methodological point of view. Generally, what you would like is to have a lot of feedback while you're going along and keep testing if each component that you're replacing is still doing the function that you want it to do, etc., and whether this has some large-scale effects. But anyway, there's some really good results in terms of the scanning. This is the knife-edge scanning microscope. This is from the Yunsuk Cho lab. And what you see here is just a little piece of volume from rat brain, and it's showing some pyramidal cells in there and their connections. Right now, the state of the art is in fact that they can scan an entire mouse brain. They've done this for the vasculature so far, but they're going to do it for the dendrites and axons and the neurons very soon. Right now, in fact, they're doing a neural scan of a zebrafish, though I'm not sure I can talk about all the details there. It has something to do with this commercial group there, 3Scan, that's going to be using the knife-edge scanning microscope as well. I should quickly mention the scale there. So a voxel, in this case, is 0.3 microns on each side. That's the maximum resolution they can get out of this. That's enough to see neurons. It's enough to see most of the parts of the axons and dendrites. It's not enough to see synapses. Then we have the automated tape-collecting lathe ultramicrotome. That's the work of the Lichtman lab, and mostly the work of Ken Hayworth, in fact. He's developed several different prototypes of this system, and now he has a very good one that's based on a lot of off-the-shelf components and quite cheap to build, actually. And it can work at, well, it basically creates a library of slices or of little pieces of brain that are put on a tape. So he can store them and use them many times over and do repeated imaging. So you don't throw away the original sample, as in the knife-edge scanning microscope, which is something I forgot to mention. And here you can use electron microscopy, for instance. And in this case, what you see pointed out with the arrows here, those are little vesicles inside the synapse there. This part here is a synapse. So that's definitely enough to get at a lot of the microstructure in the brain. And Denk is using array tomography, but I don't have any images for you of that. Now, another approach that also relates to the whole brain emulation technique is functional analysis and emulation. So this is where we're not relying on structure alone. Examples are where you use microelectrode arrays to record from organisms. In this case, this is an example with snail limnea. It's work that Peter Passaro is carrying out, specifically with the notion of eventually working towards uploading. And what you can do there is you can study the function of the cells that you can record, and at the same time carry out a mapping towards a functional connectivity. So you've got some function and you've got some structure. Neuroprosthetic devices also fall in this category. I won't talk about any of those specifically, except to mention that Ted Berger is the only one who's building a cognitive neuroprosthetic, a replacement for a piece of CA3 in hippocampus. And that's really interesting work, I find. Now, a totally different technology. It's what we've decided to call demux trees. The idea here is that, well, as in Linus, Rudolfo Linus' example, the idea is to put nanowires in the brain, basically just snake up all of the vasculature and lead up to all of the axons, the neurons, and maybe even the synapses, and be able to record from them. And what you see here is actually a depiction of the size of nanowires that were developed at New York University by the Linus lab. And that red dot there would be a wire like that, and it's inside a small capillary, and it's only about 600 nanometers across. The auto-generated version would be one in which the wires basically construct themselves rather than being inserted. And then there's the nodes-only approach, where instead of drawing out all the edges of this branching set of wires, you only put in the vertices, basically, and the vertices communicate with each other either by using some other modality that can also travel across the axons and the dendrites, or another technique that you could come up with. This is not very well worked out, obviously. This one here I really like. It's a promising approach. I call it internal agent collaborative scanning with external imaging, which needs a better name, except that I now don't want to get rid of the name because I pronounce this as IXE. So I like it. Anyway, so the idea here is next generation in vivo recording, meaning we need better in vivo recording, basically. And the better way to do it is to combine recording, to combine bringing in internal agents that can deliver a better signal to you with external imaging or external recording of some form. These agents would have a number of requirements. You would need multiple specialized agents to achieve the desired result cooperatively. You want to detect biological information of different types. You want to be able to convert it into scannable response signals, because one of the problems, for example, with fMRI is that the only thing we can see is oxygen uptake, basically. So it's not really the signal we want to look at. You want a simple distribution scheme or some way of targeting where these agents go. You want to be able to record at very many sites, and you want to be able to deduce the fine structure from electrical properties, etc., so that you also get the structural part. Now, there are some examples of this kind of IXE that have begun to crop up. One of them is, in fact, to improve fMRI by using, and in this case, I'm sort of speculating a little bit based on something that I heard from Ed Boyden recently. You could, for instance, use optogenetics to improve the specificity of readout with fMRI by only stimulating very selectively with optogenetics and reading out the result. So you can do basically electrical testing of a specific region and read out there. Another is passive nanoparticles. Some of those have been in use for a while and tested. I see there's a spelling mistake here. There's no such thing as calmoduling. And quantum dots, which I won't go into right now, but they were extremely popular for a while, and I think they still are in some areas of neurology. Then there are active nanoparticles, where the idea is that you introduce some nanoscopic changes or agents that will help you to create a better image. For instance, by reacting to the biological signal that you're trying to register and becoming impervious to the imaging beam, or by actively transmitting something. And, well, the ways to create those, there are a number of different ideas, of course. And one of these is to use synthetic biology or nanotechnology to create agents like that. The idea would be to do something similar to what we see in optogenetics, but now for recording. For instance, to have viruses that can specifically target particular cells in the brain and sit there and just kind of react to the activity that's going on. A totally different approach to trying to get to, okay, yes, I have to quit, I know. I'm almost there, actually. It is what I call brain-computer interfaces. Actually, most people call it brain-computer interfaces. It's a normal term. So the idea is become cyborgs and basically upload that way. So you start incorporating more and more technology. Then we have what I call loosely coupled offloading. The idea is there that you live with a huge array of machine intelligence that tries to predict as much about you as it can, until it basically performs all of your I/O as well, and you're in sort of total immersion. And the idea is, well, if we do this well enough, and the human is basically undergoing sensitivity analysis as a black box, then will it become possible for this machine to basically become indistinguishable from the biological parts in terms of how it acts? And in that case, can you simply sacrifice the biological part and it's okay? Well, I'm not going to comment, but I'm not a big fan of this method. And then finally, there is personalization of standardized cognitive architecture. The idea here is that you can use, this is even more general, let's say. You can use a general model of, say, perception, motor action, cognitive tasks, etc. Let's say start with SOAR or ACT-R or something like that. And then even use very general knowledge, like why would we need to remember exactly what a car looks like if we can just take images from Google or something like that that has tons of images of cars and just use those as cars, when the thing that's specific about individuals is perhaps the way that they work with knowledge rather than specifically which images they have in their memories. So, we could just try to acquire the specific aspects of how a person handles knowledge and take those things and implement them as parameters in this very generic system. And there are quite a few proponents of this approach, probably because it seems easy. Okay, so then you'd evaluate each of these with a certain number of technical requirements, which I don't have time for right now, but you can read them off the slide. And then I just wanted to end quickly by saying that there is, in fact, an effort going on to do this more strategically, to work on this project as a real project, because we think that it really has we can really do something about it now, and it embraces universal Darwinism and gives us, therefore, more, I think, long-term potential than almost any other transhuman technology you can think of. It really deserves that attention, and we have one organization called Carbon Copies, which is looking at all of these items, so literature, road mapping, networking, outreach, and is doing pretty well there. And we also have, for instance, my own employer, who is quite serious about this, and I think we all should be. I think that that we need to look at specific key questions there, and that we also have these technologies to develop further. The way I like to look at it really is as a puzzle. I like to say that a big project like this is like a huge puzzle where we know that many of these puzzle pieces are already being taken care of by mainstream research all over the place that's completely unaware of how it could be used for this. But that there are some pieces that are missing and that require focused attention, and that's where we can shine a sort of a spotlight on that. But then on this puzzle, there's also a fog, because we can only see this far, kind of up to the horizon of the next technological requirement. We can't plan it from A to Z, and then you go to the next step as you get there. So it's sort of this puzzle idea. So just to summarize, and that's the end of my talk, the universe is Darwinian. I think that the promise of friendly yet superior AI in the long term is snake oil. I don't really think we're going to get that. The best shot that we have at benefiting from AI rather than bearing its brunt is to escape catchment by seriously pursuing this advancing of substrate-independent minds. And if we look at the end result there, then we can see that those that adapt well and increase their capabilities beyond one domain win more. So I think that of all transhumanist pursuits, only substrate-independent minds embraces this and offers a possibility to escape catchment and rapid Darwinian outselection. Thanks.